let's pick up where we left off from last time, and then we'll continue on with another activity. So last time we were looking for the flux of a vector field, and we're deciding, instead of finding the flux of 4 different surfaces, it's not the flux of a curl, so we can't use Stokes' theorem. And it's not, the surface is not a closed surface. And I realized that this information over here was part of the solutions that I forgot to take out, and it was just part of the worksheet. But the idea is that it's not a closed surface, so we can't use Gauss's theorem directly. But if we close the surface, then we can use Gauss's theorem, and we're hoping for an easy flux integral of a flat disk instead of any of those 4 other surfaces that we're looking at. So I think this is as far as we got. We want to compute 2 things. We want to compute a triple integral over the solid, and the solid happens to have 4 pieces that are kind of fused together. And we're going to need to find the flux of a surface, a flat surface. All right, so let's pick it up from here. I'm just going to quickly draw the flashlight and give it some dimensions and idea. So this first page, we're going to focus on the triple integral of a solid. And we found that the div was a constant, which is great news, because you can take the constant out and you're taking the triple integral of 1 of E. So that's the div. And then the rest of the integral now would become a geometry problem where we're finding the volume of E. So what does E consist of? It consists of a hemisphere with radius 2. That's the top of the flashlight. It consists of a cylinder. And this went from what? From 3 to 10 or something? So this has height 7 and a radius of 2. And then we have a part of a cone with a radius 2 and a radius of 4, was it? And then the height of this is, do you remember? It was from 1 to 3, so it has height 2. And then we have one more cylinder with a radius equal to 4, and then the height is from -1 to 1, so the height of that is 2. So this, by the way, is just going to equal to 5 times the volume of E. And then E happens to be 4 different solids. So, well, we can do that when we're dealing with the flux. We can deal with that separately. So we have half of a hemisphere. So area of E1 equals it was area of volume. Sorry, it's volume. I should put volume here. It's 4/3 pi r cubed times 1/2, because you're not dealing with the whole sphere. So this becomes 2/3 times 8, 16/3 pi. Then a cylinder. The cylinder is, what's the volume of the cylinder? Pi r squared h. So pi r squared h. So 28 pi. I think the next one is a tough one. Well, I don't know. It's tougher than the others because we need to find the volume of a cone and then take out the other cone, or take out the top part of the cone. Or you can integrate, but let's just find the volume. I think we need to figure out the height. So we know that this is, the height here is 2. And we know this goes from a radius of 4 to 2. So would this be another 2 units up here? Is that correct? Am I doing my geometry right? So the big cone is essentially a height of 4 and radius of 4. What's the volume of a cone? I don't even know what that is. Pi r squared h. It could be found easily. 1/3 pi r squared h is the volume of a cone. So if we take the big cone, subtract off a little cone, the big cone is 1/3 pi r. The big cone has radius 4 and height 4, minus the little cone has radius 2 and height 2. I'll give this volume in here. So the whole thing is just 56 pi over 3. And then the last volume is a cylinder again. So again, it's pi r squared h. R is 4, h is 2, 16, 32, 32 pi. All right, I think we got something. Let's put it all together. We got the triple integral over the solid of the div of f dv is equal to 5 times just the sum of these things. So it's 16/3 pi plus 28 pi plus 56 over 3 pi plus 32. All right, so if we, I guess, simplify this, it would be a number pi. What is it? Well, it's 84 times 5. Is it 120? That's not 120. 420. All right. That's the first part. Let's get to the other integral that we have to do, which is a flux. So let's, the second part would be the flux integral over this new surface. Was it S5 or something? I think we called it S5. We have to remind ourselves, I have to remind myself of what the thing was. I got it here. And we want the surface to be the disk of radius 4 that has a z component of -1. So there's a couple ways to do this. We can jump in and make this polar right away, or we can use x and y and then use the domain. I think if we use x and y like we've been using, that'll work as long as we identify that our domain is going to be that disk, a circle of radius 4. So that when we go into polar coordinates, we would know. So the x and the y are just going to be the parameters, and then the z is constant. Z is -1. And the normal vector, let's talk about the orientation. What's the, the orientation would be straight down, right? So this is this disk that's below the xy plane. It's at the z is equal to -1 level, and we want our normal vector to be going straight down. Because if you imagine this being the cover of the flashlight in front, then the outward normal would be going down. Yeah?
So the light would be going through that little slit on the bottom?
Yeah.
Since it's traveling going down there.
Well, that's not the reason why it's going down. The reason it's going down is because the outside would be pointing away from the flashlight, right? So if I redraw the flashlight, all your normal vectors are going out. And so for that surface, the normal vector needs to be going out, which is, in this case, going down. So I think that would give us a nice n. So -k probably would have been easier, but I'll put 0, 0, -1 since that's how I've been writing all my vectors. Which is kind of important for us because that means when you dot this with the vector field, the first two components won't matter because it's going to get dotted with 0. And then so all we would have is the z component. So let's work that out. We got f with your r of x, y in there, dotted with your n. So let's figure this out. I'm going to put, since when you dot them, the first two components will be not significant, I'm just going to put star, star, and then the z is 5z. dotted with 0, 0, negative 1. So this is negative 5z. Now what's z equal to? Z is equal to negative 1. So this gives us positive 5 for our double integral. So we get into our double integral over the domain D, and we have a 5 over here. And then our ds or dA now is going to be, well, dependent on this circle. So take the 5 out, dA, 5 times the area of D. The area of D here is pi r squared, r is equal to 4. What is it? 80? No. 80? Is it 80? No. 16 times 5. Okay. So that turned out to be fairly easy to compute, right? And this really helps having a flat surface that's parallel to one of the components or one of the coordinate planes, so that your vector, your normal vector, will have a couple of zeros in there. That'll easily wipe out a couple of components. So finally, let's put our finally here. So it turned out that the flux of the whole surface, and I think the whole combination of S1 through S4 is just S, is equal to the triple integral of the solid E of the div minus the flux of the new surface, the fifth surface that we put on. And then we got 80 pi for this and 400 and something. For what? 420 pi for the volume one. And this becomes 340. Okay. So we had an open surface, we closed it so that we can take advantage of Gauss's theorem, and then stuff happened. Well, it's all in here. All right, any questions? So you guys know about the, yeah.
Okay, so for this particular question, how did we determine that we were taking the volume of the solid and subtracting that small?
Because, well, we weren't sure if we're going to take the volume of the solid, but we for sure knew that we were going to do a triple integral because of Gauss. And since the surface was open, we knew that we had to cover up the surface so that it's actually a closed surface. And we can't use Gauss's theorem if we don't have a closed surface.
I see. So we just basically added the bottom part of the function.
Yes.
So this would be Gauss's theorem right here. So the Gauss's theorem takes in the line.
Well, Gauss's theorem looks like this. It's you need to. It's I'm gonna write it slightly differently. I'm gonna write it with the triple integral first, and then this becomes a double integral. Now instead of S over here, I'm going to call it the boundary of E, which is a closed surface. It's a surface. So this is a flux integral. The original vector field, ds.
And then we can, depending on the situation that we're dealing with, that integral may be harder or easier than
Correct. Yeah. And in general, this is the easier integral because you're integrating a simpler function. Generally, when you take derivatives of stuff, it becomes a little simpler. And in this particular example, it became super easy because it's a constant. Okay.
So in that gradient, I'm just trying to recall. So that gradient vector is just the partial.
The div.
Oh.
Right. So the div was the partial of this with respect to x,
Okay. Zero.
the partial of this with respect to y, and the partial of this with respect to z.
Okay. Got it.
Okay.